Good evening. On behalf of the University of Mount Union and the Faculty Development Committee, it is my honor to welcome you tonight to the annual faculty lecture. I'm Sandy Madar, and I'm the founding dean of the College of Natural and Health Sciences. The faculty lecture is just one of many edifying events Mount Union hosts each year. This one is special because it highlights the work of our exceptional faculty, who conduct research, make creative works, and engage in scholarship in their disciplines. In a year when so many things have changed for us, we're very fortunate to be able to gather tonight for this important discussion. We're glad to have those of you that are in the audience virtually as well. Mount Union students hear about and benefit from the work their professors do in their classes, but the faculty lecture allows one of these outstanding faculty members to share some aspect of their work with the campus and the local community. Tonight, we welcome Dr. Robert Woodward, Associate Professor of Chemistry and Biochemistry at the University of Mount Union. Dr. Woodward earned a Bachelor of Arts degree in chemistry, a Bachelor of Science degree in biology, and a Doctor of Philosophy degree in synthetic organic chemistry, all from The Ohio State University. He was also awarded the Mount Union Great Teacher Award in 2015. Woodward has been a member of the Mount Union faculty since 2012. Dr. Woodward will present The Microscopic Enemy Among Us, Antibiotic-Resistant Bacteria and Humanity's Response. He will discuss the emergence of antibiotic resistance in bacteria and how humanity is responding using novel approaches in the laboratory, healthcare facilities, and antibiotic marketplace. Bob has already presented on this research with his scholarly community, and perhaps most important for the purposes of this audience is the fact that he presented both on the science of his sabbatical, but also how he plans to integrate some of the research needed to move his agenda forward in the undergraduate curriculum. I appreciate that Bob laid out a 10-year plan, as it is true that such work, particularly when involving students, requires a long view. Please help me in welcoming Dr. Robert Woodward to the podium to present the 2021 faculty lecture. Recall, before we start, and he'll mention this as well, that if you have questions, they may be submitted on the link provided on the announcement for the lecture in UMU today. If you're in the audience, there's also QR codes that you can see on several of the podiums, and I believe that QR code will be shared at the end of your lecture as well. Without further ado, let's welcome Dr. Woodward.
Well, good evening. Thanks so much to everybody for coming out, and thank you especially to the Faculty Development Committee for affording me this opportunity tonight. It really is an honor and a privilege to be able to come before the Mount Union community, both in person and virtually, and share with you what's really been a passion of mine for the past 2 decades. See, ever since I was an undergraduate, I was fascinated not just by the separate disciplines of chemistry and biology, but also the interface between them. That area where the knowledge and the principles of both could be integrated to help solve complex problems. And it's one of those complex problems that I want to speak with you all tonight just about a little bit, namely how humanity can combat the rise of antibiotic-resistant bacteria. Now, I think at least to some degree, all of us are familiar with antibiotics, right? So these are just medications that we take when we get an infection from bacteria. In other words, when a bacteria, like this little guy right up here, well, here he is, when they get inside of our bodies and they cause an illness, well, we take these medications to either kill them or to just prevent their growth and multiplication. So, for example, I imagine that most of us here have had a time in our lives where we've had some particular ailment pop up and we've gone to see our physician to receive a prescription for antibiotics. And that's a pretty common mode of action because in 2016 in the United States, over 270 million prescriptions were written for antibiotics. That's enough for 5 out of every 6 Americans to have received a course. And so it's not just, though, for these minor kind of maladies that maybe we experience on an average basis that we utilize antibiotics, but rather they also make possible many aspects of our healthcare that we probably take for granted. For example, it's antibiotics that make it possible for over 1.2 million women each year to deliver their children via C-section without having to worry about getting a post-operative infection. It's antibiotics that make it possible for over 650,000 people each year to receive chemotherapy as outpatients without having to worry about their weakened immune systems trying to combat a bacterial infection. It's antibiotics that make it possible for nearly 40,000 people each year to receive organ transplants. So it's clear that antibiotics are an integral and incredibly beneficial part of our healthcare, not only here in the United States, but also around the world. But unfortunately, there's a problem. See, a lot of these bacteria that we try to target with these antibiotics, some of them, they've stopped responding to the drugs. In other words, they've become resistant. They've kind of conquered the medication, you could say. Now, this is a significant problem in light of what I just mentioned about things like C-sections and chemotherapy and organ transplants. Because this rise in resistance, what it can do is it starts to shift the risk-reward balance more towards the risk side, such that eventually, if this problem persists, you start to wonder, how good of an option is it to have some of these procedures performed that we talked about earlier? Could we potentially return to the dark ages of modern medicine before they were even possible? So that's the topic that we're going to be exploring tonight, how we could overcome this increasingly prevalent issue of antibiotic resistance in bacteria. So to do that, there's really three key questions that I want us to talk about tonight as we move through this. First, what we want to look at is, well, how did antibiotics actually become such an integral part of our healthcare here in the U.S.? And then once we understand that, we can start to understand, well, okay, then how did the bacteria respond in turn and ultimately conquer one of our greatest achievements? And then facing that, we can finally address the question of, well, how should we respond? So let's take a look at this first question here. And it's a particularly interesting one because really when you consider the history of antibiotics, they're not that old. They didn't really start to come into full force until close to the 1930s. See, prior to that time, we were in what could be considered the pre-antibiotic era. And so before 1930, for really the past 2,000 years, Western medicine had been dominated by something known as the Humoral Doctrine. Now, the Humoral Doctrine basically posits that health is a sign of balance. And so if you're sick, that's a sign of an imbalance of something. And so this doctrine said that those four somethings were blood, phlegm, yellow bile, and black bile. And so if you had a particular illness arise, the idea was, well, we need to do something to correct the imbalance of that. So that's where you would see devices like this come into play up here, a device that was used in a process called bloodletting, which this is a spring-loaded device that basically punctures the skin with small razor blades so that the physician can then remove some of your blood, thus restoring your humoral balance. Now, I think we would all look at this and think, this is a pretty barbaric practice, and it seems really unfounded. Why would somebody do this? But you must understand that at the time, there really wasn't a good option. You had surgery that was a possibility, but throughout most of history, that carried with an incredibly high risk of infection and thus mortality. Also, the only other option was then to really follow the words of Hippocrates and do no harm. But most people want something done. They don't want you to just do no harm and not help them out. And so they were willing to move into the line of thinking that the Humoral Doctrine espoused. So that's the way it really was up until the first half of the 20th century. And then something suddenly changed. And this is one of my favorite stories to tell in the classroom. It took place actually in a family's home in Germany in the 1930s. There was a 6-year-old girl named Hildegard Damik that was walking down the stairs one day. And she tripped and fell, right? Kids do that. I've got 4 of my own. They always fall down. But unfortunately for her at the time, she was carrying a sewing needle in her hand. And so when she fell, the needle penetrated her hand, eyelet first, and part of it snapped off inside her hand. Now, the family physician came over, removed the shard, but within days, she had a fever and she had an infection running up and down her arm. So over time, as they started to monitor, her condition just continued to worsen until finally her physician recommended to her parents that her arm be amputated. Now, for those of us that are here, or that are watching, that have children, just imagine what that would have been like to be seeing your child suffering, moving closer and closer to death, and knowing that your only course of option was to have her arm removed in a procedure that may very well ultimately cause an infection and potentially death in and of itself. What do you do in that situation? Well, in her case, her father Gerhard, he took some rather drastic, and I think you'll understand here in a minute, what we'd probably consider pretty unethical actions today. See, at the time, he worked for a company known as IG Farben, one of the world's largest chemical companies. And they specialized in a lot of different products, but particularly dyes. And not just dyes for the applications in clothing, but by that time they had also realized a couple of important things based on some discoveries. First, it was known that many illnesses and many infections were caused by bacteria. Secondly, it was also known that you could color certain types of bacteria different colors, a process known as gram staining. And so with that idea in mind, the folks there started to wonder, well, perhaps we could actually, if we can get a dye to target a specific bacteria, maybe we can make a drug that could target a bacteria and not just turn it a color, but kill it. And so that's what Gerhard Domik had been working on in that time, about 3 years prior to Hildegard's accident. In fact, in late December of 1932, he was running an experiment right before he left for his Christmas holiday, and he set up 2 litters of mice. And 1 litter of mice, he injected them with 10 times the lethal dose of a particular type of bacteria. The other litter of mice, he injected them with the same dose of bacteria, but he also injected them with an experimental dye known as Pronicil. So he went home, went on holiday, but as any good scientist, curiosity got the best of him, and so on Christmas Eve, he slipped back into his lab to see what was going on. Now, not surprisingly, the mice that had received just the bacteria, they were all dead. But the mice that had received the bacteria and the dye were all alive. And so he was incredibly excited by this finding. And he wanted to, get this going with clinical trials right away. And they did get some preliminary work done, but the work kind of stagnated. There were some issues with the clinical trials, and it just never got to the point where it was actually approved for use in humans. But when he was sitting there 3 years later, watching his daughter suffer, he couldn't get that experiment out of his mind. And so he made a decision then. And he slipped back into his lab at IG Farben, and he stole a few vials of the drug, and he took it home, and he started injecting his daughter with increasing concentrations of this experimental dye. Now, initially her condition worsened, then her fever started spiking and crashing, but then, exactly 3 years to the day after he had started that experiment with the mice, his daughter's condition stabilized. And she was go on to live with both of her arms intact. And so this dye, or what would ultimately come to be found to be the drug sulfanilamide, it really set off, along with Alexander Fleming's more well-known discovery of penicillin, they really set off this just boom of antibiotic discovery in what can be termed the golden age of discovery, really for the next 40 years. And so this was a time where all of a sudden you saw the medicine that was available catching up to many other aspects of the society that had started to become more modern, such as transportation and communication. So this boom in antibiotics that was seen was really led through 2 distinct pathways. We find one pathway for the discovery of antibiotics relies upon work done in the laboratory, kind of like in the case of Pronicil, where you make a bunch of different chemicals, a bunch of different compounds, with the hopes that perhaps one of those in this huge library is somehow going to be able to kill off a bacteria. And then if maybe you get a hit, then you can refine the structure, and eventually, hopefully, you'll get one of these drugs, which is one of the new classes of antibiotics that came out since the year 2000. Alternatively, if you think back to Alexander Fleming's discovery of penicillin, he found that because, a fungus had contaminated a petri dish of bacteria that he had. And he realized that fungus was giving off some kind of compound that was killing these bacteria. Well, ultimately he discovered that was penicillin, but more importantly, this led to the idea that if you look out in nature, there's lots of natural products that could potentially act as antibiotics, particularly from microorganisms such as bacteria in the soil, because they make these compounds because they want to defend themselves against other bacteria. And so you then start to see scientists going across the world to collect soil samples from various habitats. In fact, it's often said that two most important groups of people in that area for discovering natural products were pilots and missionaries, because these were people that were in these diverse habitats around the world that could get these unique samples that contained these unique bacteria. And so through these two pathways then, there were just hosts of different classes of antibiotics that were discovered. And what was particularly powerful about them is that they didn't just all target the same thing. They attacked bacteria in a few different ways. So, for example, if we take a look at how it does this, now we looked at bacteria earlier in kind of this cartoon format here. But let's take a look at a more real-world perspective of it here. There we go. So if we kind of put this version now in cartoon form, we can get an idea of how bacteria or how our antibiotics are actually attacking these bacterial cells. Now, one way you might imagine is basically through compromising kind of the structural integrity of the bacteria, right? Imagine you've got a balloon. If you have a balloon and you take a needle and you stick it at the balloon, it's going to pop, right? Because you're compromising the structural integrity of that balloon. In the same way, we can target these areas here, the cell wall, and then inside of that, the cell membrane, so that the bacteria essentially won't be able to function properly. One particular example is amphotericin B. It basically just creates a hole, a pore in the membrane, which causes it to be leaky. Things that are supposed to be inside are getting out, and so the bacteria is not able to persist. Now, alternatively, we can interfere with things that are going on inside the bacterial cells as well. And we see that with the example here of perhaps interfering with processes related to DNA, for example. Because every time a bacteria replicates, kind of like when we replicate, we have to pass on DNA. Well, so do they. Well, if we can disrupt that process, well, they can't undergo that replication. Alternatively, we can also attack protein synthesis, or their production of molecules that are necessary for their survival, for cell division, for all kinds of key things that go on with them. Or we can target metabolism, so kind of their turnover of molecules that are present within themselves, such that then you're not able to then make key materials like DNA. So we've got a whole host of different mechanisms here that can be investigated. And we have a whole host of antibiotics that are causing these mechanisms of action to happen. And so that's all great, but unfortunately, even though we were having such success at this, around 1960 the pace started to slow a little bit. And you see here this huge lag period that actually occurred from the 1970s through about 2000. Now, the reasons for this, there's a variety of them. Some part of it was probably complacency. I mean, we had so many antibiotics that worked in so many ways. I mean, we were really proud of ourselves, and we thought we have a really complete antibiotic arsenal, so we've got enough. Also, the pharmaceutical companies looked at this, and they were having some difficulty coming up with broad-spectrum antibiotics. And by broad-spectrum antibiotics, I mean drugs that not only target one particular type of bacteria, but antibiotics that can target many different types of bacteria. So if you think about that from a pharmaceutical company's perspective, that's a good thing, because that means you make one pill and it can be used for a variety of illnesses. And so that's going to translate into a lot of revenue. Now, at the same time, though, these pharmaceutical companies, they were starting to find a niche in being able to go out and treat chronic medications. So things you needed maintenance medications for, such as depression and anxiety. So they knew then that you were going to need a pill a day, essentially, for those, and so they would invest more readily in those. So this was a problem in some ways that we were not having discovery going on, but in and of itself it wasn't a huge deal because we still had a lot in our arsenal. But there was one complicating factor that proved to be really detrimental. And that was at the same time that all this was going on, these green boxes here are showing that resistance to these different drugs began to emerge, especially during that lag period. So what that meant was, all of a sudden, bacteria, they were a step ahead of us. They were coming up with ways to fight off our antibiotics while we were not developing new antibiotics to try and combat them. So how do they resist our antibiotics? And that's really getting at our second question for tonight. How did they overcome what had been a really great achievement that humanity had made? Well, there's a few different ways that they do this, just like there's a few different ways that we attack bacteria. So one way is bacteria actually have what you could consider a dormant. Right? They have, what a dormant is, right? Is somebody maybe stands outside of an apartment complex and regulates the flow of traffic. Some people are able to come in, not all people are able to come in, and so they're kind of the guardians of the doorway there. And bacteria also have a similar sort of dormant, so to speak. These things shown in the bottom right here called porins. Now, under normal situations, when we have an antibiotic that works against a bacteria, the antibiotic can go through that porin and get to the inside of the cell. But bacteria, they figured out, well, maybe we just need to switch our dormant, so to speak. And that's exactly what they did, and they mutated their porin proteins so that now this resistant bacteria, it won't allow the antibiotic to access the interior of that cell. So it's just keeping it out. And so what we see here then is this decreased permeability where the antibiotic can't even get into the cell in the first place. But sometimes, we can outsmart them. We can still get our antibiotics into the cell. So what do bacteria do when the antibiotics actually successfully get into the cell? Well, they turn on their sump pumps, right? I mean, these are things that we use to keep water out of our basements. Water comes down the foundation, we pump it off site. Bacteria do the same thing when antibiotics get into their cells. They actually have these things right here, these efflux pumps, that when the antibiotics make their way in, they pump them right back out. So just by those two measures then, they're doing a good job of just keeping the antibiotics out there. But they're not effective for all antibiotics, and not all bacteria have these suitable systems. And so they need other ways then to get around this problem. So another way that they can do that, once the bacteria actually, or the antibiotic gets into the cell, and it starts to get to where it's going to attack the bacteria and shut down some process, well, the bacteria realize, okay, instead of presenting my particular enzyme to you as it normally would be, I'm going to tweak it a little bit. In other words, what they do is, normally your antibiotic would come in and it's kind of like a round peg fitting in a round hole. It fits. It works. We can shut down something that the bacteria is doing. But they switch it out on us. All of a sudden they give us a square hole. So then you get a round peg coming in and it's not going to fit through that square hole, right? And so because of that then, the antibiotic, it's just kind of shooed away. It's not interacting with what it's supposed to be interacting. It can't shut down any of the processes. But if that's not enough, bacteria have also come up with ways that they can essentially deactivate, or basically chew up our antibiotic and spit it out. In other words, they can modify our antibiotics so that they're no longer effective. So they've done a good job then of responding to us as we developed all these different classes of antibiotics. But how did they do that? How did this resistance suddenly spread and go to these bacteria that previously we'd been able to kill off? Well, there's a couple of ways they can do it. One we're pretty familiar with already. There we go. Known as vertical transfer. Now this is what we usually think of when we're passing traits on, passing our genetic information on in terms of humans, right? We have particular traits that we pass on to our children. In the same way, bacteria will do that. If they have a particular gene here, say in red, that's a resistance gene, they can pass that along to their offspring. And then their offspring can pass it along to their offspring. And so by doing that, you've now propagated that resistance gene and it's spread amongst the population. So this can happen kind of randomly in some situations when the bacteria are replicating. They'll get a mutation that maybe gives them a little bit of an advantage. And because bacteria reproduce so quickly, they're able to spread it out and gradually get a pretty sizable population of these resistant bacteria. But where bacteria are unique and particularly challenging is they not only pass it on to their kids, so to speak, but they pass it on to each other, to currently existing populations, through this process of horizontal gene transfer. They do it through a variety of ways because, sometimes there can be, if a bacterial cell dies, it'll release its DNA, and another bacterial cell can pick it up through this process of transformation. Or sometimes you can actually get bacteria that mate with each other in a process known as conjugation, and they pass DNA along that way to each other. Or you can get one of these nasty little critters here known as a bacteriophage, and it's actually a virus for bacteria, and it can take DNA essentially from one particular bacterium and it can transfer it to another. But the idea here is through all these mechanisms, what's happening is we're allowing resistance to spread across bacteria. And that's a really dangerous thing because we're seeing that it's having some pretty significant impacts on our health. We see that an estimated, as of last year, 2.9 million infections caused by antibiotic-resistant bacteria. We also see close to 36,000 deaths caused by that. And so this is a particularly challenging issue that we have to think about, especially when you consider the worldwide implications, where it's estimated you have 700,000 deaths resulting from AMR here, or antimicrobial resistance. And the projections are that if the current burden of antibiotic-resistant microbes continues to expand at the rate it is, we're going to be looking at 10 million deaths due to this by the year 2050. So this is a huge problem then that we have to think about. And it leads us really to the other piece that I wanted to talk about tonight. And it's that in light of these challenges, in light of everything that's going on here, how are we going to respond? How can we come back, overcome bacteria? How can we reposition ourselves in this fight, in other words? So there's a lot of different approaches to it, but I do think it's important we have a multi-front approach. We don't want to be just developing new antibiotics, for example. We need many things going on at once. And tonight I want to focus on three specific areas: responsible use, research innovations, and revitalization of the marketplace. So let's take a look at this first idea of responsible use. And when I say that, what I'm referring to is the idea that we need to be better stewards of the antibiotics that we currently have, as well as those antibiotics that we'll undoubtedly one day have through future discoveries. And perhaps one of the best ways to think about antibiotic stewardship is to consider how we've erred in the past, because we have made some significant errors when it comes to specifically how prescriptions are being handled. So for example, in this study from 2018, the CDC indicated that while 70% of antibiotics were given out appropriately, 30% of them were not. Now, when you consider that over 270 million prescriptions were handed out around that time, that's a huge number we're talking about with that 30%. And so we really have a problem here with what we could term unnecessary use. In other words, putting the antibiotic out there when it's for something that it's not going to be able to successfully treat, such as a viral infection. But in addition to unnecessary use, we also have a problem with the duration of the antibiotic prescription, how long your course of treatment is. For example, another piece of this study indicated that while adult sinus infections should be treated with a 5 to 7 day course of antibiotics, 70% of people were given a 10-day course. So we've got a second problem here then of excessive use, using it more than it needs to be. And so these issues of unnecessary use and excessive use, when you put them together, really what they're doing is they're taking antibiotics and they're putting them out there in the environment more than they need to be. They're exposing bacteria to them more than they need to be, and you're heightening the potential that resistance is going to develop among them. Okay? Now, I share this data tonight not to point fingers. I'm not picking on providers. I mean, my wife's here in the audience tonight, and she's a pediatrician, so I'm not pointing fingers. I don't want to sleep on the couch tonight. But what I am doing is I want to offer this up as evidence to say, how can we move forward? What concrete steps can we take to change the course of what we're doing? And the CDC has played an important role in doing this already through the development of antibiotic stewardship programs in hospitals. Specifically, they recommend a series of 7 core elements here that can really help make these programs successful in hospitals. So the first is you need to have leadership commitment, right? You need to have the resources, whether you're talking about human, financial, IT. You have to have all those elements in place if you're going to do this. Then you're also going to need accountability, right? You need a point person who's going to be somebody that's going to answer for what's happening. But you also need, beyond just a general point person, you need somebody that has the drug expertise. Somebody that is, perhaps a pharmacist that's going to be able to help give those recommendations of how to improve antibiotic use. Because you need action as well. You need specific steps that can be taken to help your hospital improve in this area. And you need tracking, right? You need to keep track of how many prescriptions are being given out, what resistance patterns you're starting to see in the hospitals, so that you can then report it back to the physicians, back to the PAs, back to the nurses, not in a punitive way to punish them for anything, but rather to make them aware of how much they're giving out. And then eventually you also need education. Because as science continues and you begin to make new discoveries, recommendations could change. And so you want your providers to be aware of those if those come out. And so we're doing a good job then. We've taken some good steps here from a human health perspective. And we're really starting to see some benefits of this approach, because when they first started monitoring this back in 2014, only about 41% of hospitals that responded indicated that they met all 7 core elements. But then after a few years and some further programming, by 2017, that number was up to 76%, and then it broke the 80% threshold the following year. Now, the ultimate goal was to have it by 2020, to have 100% of hospitals that were able to have all 7 of these core elements in place. But we're still waiting to see what that data tells us. But nevertheless, we're seeing some good trends here in getting these programs in the hospital, but also we're starting to see their impact. So a study from Blue Cross Blue Shield showed that gradually over the time these programs have started to become more common, you're seeing a decrease in the antibiotic prescription fill rate among those that are insured. And so it's giving credence to this idea that, yeah, we can make an impact. We can start to drop the amount of the amount of prescriptions that are being handed out and be better stewards of them. So that's good, and that helps. But we're confronting a really, really challenging issue here in dealing with 2.9 million infections, 35,000 deaths. So stewardship efforts are great, and we have to continue them. But like I mentioned earlier, we need to complement them too. And that's where we also need to think about some research innovations, or new ways that we can think about targeting bacteria to help us out along the way. So I'm going to talk about 2 particular examples here tonight. The first one is in the vein of developing new antibiotics, but not just new antibiotics, durable super antibiotics. So what I mean by that is, let's imagine, for instance, that you're coaching in the NFL, right? It's a logical jump here for all of us in the audience. You're coaching in the NFL, and you're approached to become an offensive coordinator for a particular team. And your first task is to go out and find a quarterback who's going to instill fear in defenses across the league. So you go out, maybe you find somebody like the Rams did. You find somebody with a big arm like Matt Stafford, and you think, okay, now I'm going to have a great passing attack, and I'm going to be able to just terrorize the league. Well, then your conference rival gets wind of what you're doing, and they go out and they acquire all the best defensive back talent from around the NFL. Suddenly, your return on your investment is not going to be very good. So then you start thinking, well, what if I could find a quarterback that had a big arm and had the running ability of, say, Russell Wilson? Maybe then I'd have a better shot. In other words, what if you could go out across the league and assemble the perfect quarterback? Somebody maybe with the mental awareness of a Tom Brady, right? He did pretty well last night. Or the competitiveness of Aaron Rodgers with the arm of Matt Stafford and the mobility of Russell Wilson. If you could put all those traits into one quarterback, your conference rival is not going to be able to go out and get the defensive talent to help stop an attack like that. And this is the exact idea that on the antibiotic side, Dale Boger's lab out at Scripps Research Institute did when they sought to develop a new and improved version of the antibiotic vancomycin. So this is the structure of a vancomycin derivative. I'm not expecting you to fully understand the structure, but I highlighted 3 key areas to talk through how they kind of approach this. So one area here with this X is where they made just a pretty simple replacement. They took an oxygen atom and they replaced it with a nitrogen and a hydrogen atom. And what they did by doing this is they actually overcame the key resistance mechanism that bacteria use against vancomycin, where they actually switch out an important biomolecule that's used in the production of their cell walls. So by replacing that oxygen with a nitrogen and hydrogen, now this particular derivative could target both sensitive bacteria and the resistant bacteria. It did it all equally well. But they went further. They instilled a couple of other pieces down here and up here that added a couple of new modes of action into this one antibiotic. This piece down here kind of essentially pokes a hole in the membrane. It makes it leaky. It's like popping the balloon again, that kind of idea. This piece up here, it actually comes from another antibiotic, and it still works against the production of the cell wall that gives the bacteria that structural integrity, but it targets it in a unique way. So now what this drug had done is it had pulled together 3 unique ways to attack a bacteria all at once. And the impact was astounding. They found that this drug was 10,000-fold more potent than vancomycin, which that's great. But if you go out and start giving this drug and then a year later there's resistance to it, you didn't really accomplish much, right? So what they wanted to see is, would this drug also be durable? In other words, could it fight off the development of resistance from bacteria? And so that's what they looked at with this study, or with this particular experiment here. And so I'm going to walk us through this. So on the x-axis here, we have this idea of passages. And basically what that means, that's the number of times that they exposed the bacteria to a relatively low concentration, a sublethal concentration of this drug. Because they wanted the bacteria to see it, but they didn't want all of them to die, because they wanted to give them the chance to try and develop resistance. So they would expose them once, we'll let them grow up, then they'd take a small amount of that, expose it again, let it grow up, and they continued doing that for 50 times. Now normally when that happens, you would expect to see a line, such as for this antibiotic right here, that gradually works its way up. Because what's happening here, what's increasing as we look on the y-axis here, is a quantity known as the MIC, or the minimum inhibitory concentration. In other words, that's the minimum amount of antibiotic you need to stop the bacteria from growing. And so by applying then this kind of exposure, serial exposure to this antibiotic, what was happening to daptomycin was, well, the minimum inhibitory concentration was steadily increasing. In other words, you needed more and more of this antibiotic to have an impact. So that's a bad thing. But when they switch to look at their molecule, shown down here, you can see there's barely a blip of an increase. Very modest. And vancomycin is already actually somewhat of a durable drug, so to see this was an incredibly promising result. So this idea then of having drugs that are not only effective but durable is a great strategy moving forward. Now, alternatively, rather than just making new antibiotics, another approach, and it's actually the one that we're working on in my research lab, is thinking about, well, perhaps rather than creating a new antibiotic, what if we could shut the resistance pathway down for an already existing antibiotic, right? Because we talked about earlier, it's the resistance that allows the bacteria to persist and survive, and the antibiotic gets either kicked out of the cell or destroyed. Alternatively, what we're working on is we want to have a drug that could target this resistance mechanism. Because if we can shut it down, then there's nothing that's going to be there that will stop the antibiotic from going on and killing off the bacteria. So this is a similar idea to what you've seen if you've ever heard of augmentin, for example. It's basically a combination of an antibiotic and a molecule that shuts down a resistance pathway. And so that's what we're working on with an antibiotic known as vancomycin. So we've got these ideas then of how we can go out and we can improve, in terms of designing new approaches to targeting bacteria. And all of that's great, but that takes us to the final piece of this multi-front approach, and probably the most challenging piece, because it brings up the question of who's going to pay for all this work? Now, normally, when you think about this, if you're developing a new drug, it's going to be the pharmaceutical companies that are going to pay for it, right? They're going to put in the upfront investment, they're going to go through the years of development, and then in the end, they'll make a nice return, a nice profit on their investment. But unfortunately, right now, there are some complicating issues. Specifically, what we're seeing is that companies are really lacking the incentive to invest in antibiotic discovery efforts. Now, one reason why is this chart that I just talked about being such a good thing earlier. But for companies, this is a bad thing, right? Improved antibiotic stewardship, if you're not using the antibiotics as much, well, that means the volume of sales is going to be lower, and that means the revenue is also going to decrease. Furthermore, when new antibiotics come out more and more, they're being looked at as drugs of last resort, so to speak. In other words, you want to keep them on the shelf and only use them when you have to use them. So in a healthcare setting then, antibiotics have great value, even if they're just set aside like that. But from a pharmaceutical company perspective, that's a terrible thing. Because if you're just setting it aside and not using it, you're not going to get rewarded for your volume of sales. And so because of that, your profits are going to decrease. But additionally, like I mentioned earlier, companies have also found success or security in chronic condition medications. So treating depression, treating anxiety. Because then if you're having to take a pill a day and they know that that's going to be happening, well, they know there's a guarantee for some pretty significant revenue there. So it's worth the upfront investment. So there's really two challenges then that we're looking at here, because number one, we're seeing a lot of the companies in big pharma, because of these issues, they've exited the antibiotic playing field because there's just not the return there that they need. Because antibiotic development can take up to 10 years and a few $1 billion to get one drug to the market, not to mention the ones that would fail along the way. So that's a problem for them, but then that leaves antibiotic development to smaller companies. And smaller companies are going to be at much higher risk for failure. In fact, of the companies that brought antibiotics to the market since April 2019, already 3 of them have failed. So if we're going to try and think about how we can revitalize the antibiotic marketplace and make it attractive again, we really have to do 2 things. We have to think about how we can encourage the development by small companies while also trying to minimize their risk for failure. And then we also need to figure out how we can get the players from big pharma back onto the playing field. So let's take a look at what's being done to try and incentivize small companies to get involved in these efforts. So there's been a few programs that have popped up really within the last 5 years. The first one I'll talk about is a program called CARB-X, or it's the Combating Antibiotic-Resistant Bacteria Accelerator. So this was it's a nonprofit public-private partnership that was set up in which companies that are at kind of an initial stage where maybe they have an idea of a compound that could succeed, they're going to get some backing that's going to allow them to kind of move along this trajectory here, where they get to try out lots of molecules, maybe they find a really good one, and eventually they get into the initial phases of clinical development. And so CARB-X is going to provides those companies with funding from various private foundations as well as some different government agencies from around the world. And so they're able to invest in that, but they also have access to a support team of technical experts in the particular area. And that's incredibly valuable for them when it comes to these clinical development aspects, because they can't afford to keep this kind of talent in-house. They don't have that expertise there. So having that available to them is a great first step. So they can get kind of going, and they get into the first phase, but then they were kind of left to their own until this past summer. And this past summer, we saw the institution of what's called the AMR, Antimicrobial Resistance Action Fund. It's a $1 billion initiative, and it was actually set up by 20 companies that are part of Big Pharma. So they invested in this. And the idea was that they wanted to help then facilitate the later stages of clinical development with the goal of hopefully getting 2 to 4 antibiotics on the market in the next decade. And so you can kind of get this idea of now there's a pipeline set up here for these small companies. They can go out, if they maybe have a potential therapeutic, they can apply, get funding and support through CARB-X to get these initial stages of the discovery process facilitated and into clinical development. Then they can go to the AMR Action Fund after they graduate, and that will allow them to finally come out of that with a market-ready drug. And so we've got a great set of programs there to help out these small companies, but there's a problem because antibiotic resistance is increasing so quickly that it's estimated we would need about 15 new antibiotics in the next decade to keep pace. So 2 to 4 antibiotics isn't going to cut it. So we really do then need to think about how we're going to try and bring the players from Big Pharma back onto the field. And there's some ways that are being explored to do just this, one of which I'll talk about now is called the Netflix model. And so it's looking very differently at how we think about antibiotic sales. Because like with Netflix, you pay a subscription fee up front, right? You pay for a month, and you can use it as much as you want it, or you can use it as little as you want. It's up to you. Now the idea is this would do the same thing for antibiotics. Companies would sign up a contract with a particular hospital system or insurer, for example, and the idea would be they would receive fixed annual payments over an agreed number of years, regardless of how much of the antibiotic was being used. And they would get some money up front that would encourage them to develop that antibiotic. And so then, by doing that, the company is then assured of some revenue moving forward. And they're actually testing this out right now in Britain. They are looking at trying to get a couple of new antibiotics that are going to target some really highly resistant pathogens. And essentially they're offering companies, if they're selected, up to $130 million paid out over 10 years. Which sounds like a lot, but it's actually really not. Because, like I mentioned earlier, it takes a few $billions to bring the antibiotic to market. And so really what's going to be needed is you're going to need investments in these companies made by several different entities, signing similar contracts that's really going to incentivize them to get engaged and to play a role in this. So we've seen then through these 3 kind of different but complementary efforts, we really have the opportunity in the healthcare setting, in the laboratory, and from the pharmaceutical company perspective to really work together to try and combat this problem. But what about us? I mean, most of us may not fall into one of these particular areas necessarily. So what role can we play? Well, I think the good part with this one is we're at a stage right now where we can say pretty much anyone can contribute something. There's something out there that you can do. And really, as I close here tonight, I just want to offer a few practical steps that you can take to do this. You can ask questions of your provider, right? Be aware of things that are going on, how you can keep yourself safe. You can use good hygiene. I think we have all mastered that now over the last year, right? You can get your vaccinations for those bacterial infections that are out there, for which there are vaccines. And when you're becoming ill and you get prescribed an antibiotic, make sure you use that antibiotic appropriately. Also, be aware that there are some different vectors out there for transmission of these particular bacteria, whether it be animals or whether it be improperly cooked food, for example, if you're handling raw meat improperly or not cooking it to a high enough temperature. And then also, when you're traveling, you want to be cognizant of where you're going, what vaccines do you need when you go there, and are there other things you need to keep in mind, such as, well, do I need to perhaps minimize my exposure to the water supply, things like that. So by doing this then, by taking these practical steps, we can further complement the efforts that are being taken in terms of antibiotic stewardship, developing new research opportunities, and also trying to really revitalize the marketplace. And hopefully, through these all together, we can take a step forward and really reposition ourselves and put ourselves out front of these resistant microbes. With that, I thank you for your attention and open it up for questions.
right, thank you so much. Can you all hear me? We're going to move into 15 minutes of Q&A, and we've had a few questions come in today and during the presentation. If you want to pose a question, we'll see how many we can get through here as quickly as possible. Thank you again, Bob, for a super interesting presentation and very relevant. So the first question came in today around 1 o'clock. So someone who hasn't had a chance to hear your presentation but knew the topic and wanted to ask a related question. The question is, my understanding is that we rely on countries in the southern hemisphere for efficacy in things like the flu shot due to climate. But often those countries with low or moderate economies are found to be slow to embrace antibiotics. What might the rationale be for this type of paradox?
So there's a few issues that arise with antibiotic use in those types of countries. Part of it, when it comes to looking at that data, is there is kind of a reporting gap, I think, in some ways, that the methodology to access the numbers, to know how many people are really utilizing antibiotics, it's not the best in some of those areas. So some of the reliability of the data, there is some questions regarding that. But also, I think you're running into a situation where you'll have people that they can't afford a full course of treatment of antibiotics, or they can't afford to get it from the appropriate source, so they go out on not necessarily the black market, but kind of an off market to be able to acquire some of those antibiotics. And so in some cases, you're not really seeing that data getting reported. Now, in certain areas, you are starting to see an uptick in the amount of antibiotics being used. We're seeing this in the Pacific Islands specifically, where resistance is likely going to really become a problem there. And it's both due to an increase in antibiotic use, but also improper antibiotic use. And that kind of comes back to the idea if you can't afford the full course of antibiotic treatment, you're likely going to foster the development of resistant bacteria. And so those two factors, they kind of conflate each other. And so as antibiotic use continues, if there's not educational efforts that are happening there, that's going to be a bit of a challenge. Now, the CDC has taken some new steps in the last couple of years in the U.S. specifically, but it could really apply to even other countries as well, to rethink a little bit some of these stewardship efforts and say, okay, well, you're not in a position to have the resources to potentially put in all 7 of these core elements. What steps can you take to try and improve stewardship? And so it's really sifting through and trying to figure out, depending on your situation, how can we help you take steps forward in those efforts?
Okay, great, thank you. A second question that came in this afternoon from Sarah Powers. Is continuously developing new antibiotics a viable solution in the current U.S. system when pharmaceutical lobbying, healthcare costs, and subsequent medication hoarding, and a tendency to overprescribe rather than invest in preventative care and public health stand in the way?
So that's a good question. I think it ties in obviously with some of what I was talking about there, but I think it also points to, I talked specifically about antibiotic development tonight, when I was talking about research innovations. But in terms of research innovations, there are a lot of different things that I think are going to need to take place to really complement antibiotic development. One of those, I think, is going to be vaccination efforts. So the idea of developing new vaccines that you could utilize against some of these particularly troubling bacterial strains. The reason being, number one, if you're able to come up with a vaccine, you're going to help slow the transmission of those sorts of bugs. But then number two, if you give the vaccine it's effective, excuse me, then you're not using antibiotics, right? So you're slowing the spread of resistance down there. And it's been seen that, obviously the evolution of bacterial resistance to vaccinations occurs at a much slower pace, if at all. And so that's a benefit you have with those. Now, on top of vaccines, there's really some other cool approaches out there, and I didn't have time to talk about it, but I did save a slide here, just in case. Let me go to it here. Yeah, here we go. So it's on the right-hand side there. There's a company in Europe that's working on this new technology where the idea is, you may have heard of the Crispr system that's out there. So just gotten some accolades with the Nobel Prize, but the idea that they're working with here is they want to give you a drug that will be able to go out and specifically target certain bacteria. And so the idea is what will happen is they're able to target those bacteria and specifically kill those bacteria because they use these things here, these Crispr, or these guided vehicles, which they don't really say what they are because, right, it's all proprietary, so I can't quite get all the information there yet. But they put into the bacteria this particular genetic information that is going to tell the bacteria's own enzymes to go out and cut up its own DNA. And so it's kind of turning the microbes into these little suicide machines, essentially, where they're going to cut their own DNA and destroy themselves. But I think that gets at the other part of the question, too. It's the idea of we can go out and we can look at and see for each person what treatment might be best for them, so-called personalization of medicine. But along with that comes some really high costs. So that's where I think there is a balance there to be said, where if we can develop some vaccinations and have more preventative efforts against some of these infections, that's going to help with some of the burden of thinking about potentially, paying for a little bit more personalized care in some situations such as this. Plus, you're also reducing the incidence of antibiotic resistance, and so the need to continually have these new and more expensive treatments would slowly be lessened.
Okay. Darnell Tucker asked, you talked about the misuse of antibiotic treatment. What is your opinion on the role of genetic counselors in this? And do you think that there's a possibility of these counselors playing, quote unquote, gatekeepers to how antibiotics are recommended from providers?
So that's where, when I think about, this particular issue in terms of the role somebody can play in making recommendations for which is needed, there is a big push, not only from the governmental side. One of the key things that's being done is looking more at surveillance efforts and being able to get out there and work alongside that with diagnostics to determine what bacteria are causing what infection. So I don't know that it would necessarily be in the form of a genetic counselor, but I do think that you will see a shift to saying, okay, what types of resistance are most prevalent in a particular population, and then using that information to say, okay, these are the types of antibiotics that you should be recommending. Because in certain situations, it may be the much cheaper, potentially really broad spectrum antibiotic that's fine to give out because you're not seeing resistance to it. In other cases, it may not be. And they're actually looking at this in a lot of, underdeveloped countries. And the way they're doing some of the monitoring and diagnostics is by looking at sewage, because it's actually a great indicator by looking at that of what the antibiotic resistance patterns are that you're seeing amongst the human population. And so by doing that, then they can kind of give more specific recommendations on, you should be utilizing this antibiotic or you should be utilizing this antibiotic.
Great. Just a couple more.
All right.
How are you holding up?
I'm good. I'm
Okay.
good. Take another sip of water, though.
Okay, great. Dean Madar has asked, as we have begun to understand the critical importance of our own natural microbial ecosystems, what's the risk of creating super durable antibiotics that are many multiples more powerful and broad spectrum?
No, that's a great question, because you're exactly right that one of the complications that can come with antibiotics is that you're going to see problems with your normal gut microbiome. And so you have to think about what you're clearing out, because one of the other numbers I didn't put up here, because it's not specifically antibiotic resistance, but you see a lot of deaths associated with C. diff infections. And they can take hold because of antibiotic use when you're clearing out the normal gut microbiota. So that's what makes the idea of more personalized approaches, such as this one up here, attractive, because then you're not blasting everything, right? You're selecting for specific bacteria and leaving the beneficial gut microbes alone. So I think in some situations what it really comes down to is you want to think about the patient population as well, and the particular patient that you're treating. And in some cases, it may be a situation where it's, if you don't get this drug, you're going to die. And so it's going to be appropriate risk to take in that situation. But in other situations, it may not be worth the risk. So I think a lot of these drugs potentially could be more of those on-the-shelf ones, so to speak, that you're only using when you really need to use them. So it's definitely a balance, I think.
Okay, we'll end on this one. Sarah Doris asks, how do you feel this wonderful research will change or shift new post-COVID and secondary bacterial infections?
Yeah, it's funny that she mentions that, because looking at the pandemic, it's really had two kind of impacts when you think about antimicrobial resistance. Because number one, you had a lot of antibiotic use at the beginning of the pandemic because there was the concern of secondary bacterial infections popping up. And so you saw a ton of antibiotics being pumped out there, specifically azithromycin. And so that, very likely is going to lead to some upsurge in antibiotic resistance. But at the same time, when you also look at it, there has been some good motivation, I think, that's come out of it, because you've seen with the AMR Action Fund, for example, the companies that gave to that AMR Action Fund, they committed to make that investment back in 2019. So when the pandemic hit, they could have pulled out and said, no, we're going to dump our money into developing antivirals. But they didn't. They stuck with it because I think they recognized the importance of trying to plan ahead and be a little more preventative in our approach. And so that was one benefit that came out of it. But the second thing, where I think it's going to help out in a lot of ways in terms of combating bacterial infections, is some of the drugs that came out of it, like I'm trying to think of the pronunciation of it, remdesivir maybe. We'll go with that. I'll say it with confidence. That's the way. But that particular drug, it was ultimately found because it was in a library of compounds that had already gone through a lot of stages of development. And so it was in this one particular company, Caliber, had this library that you could go in and look through these. And so I think that you're going to see more of that happening, that companies are realizing perhaps we can repurpose some of these drugs that are out there and maybe more quickly respond to some of these issues that have arisen.
That'll end our question session. Thank you very much.
Thank you.
So on behalf of the University of Mount Union, Bob, we really want to thank you for an absolutely incredible lecture. You did a great job of making something really complicated approachable to all of us. And so it's no surprise that faculty, staff, and students hold you and your work in such high esteem. So we thank you for providing the lecture. And on behalf of everyone, we have a little gift here for you.
Thank you.
And with that, we'd like to close the events for this evening. And we thank you very much for your attendance.
Thank you.